Okay, this is, we looked at the truth table, right? But is that basically where we ended? All right, cool. So the whole point of all this stuff was, you know this already. And I mentioned the whole funny thing about or and how or can be confusing. So we say or and then exclusive or to differentiate the two cases. Exclusive or is only one can be true. If they're both true, it's false. Regular old or is only when they're both false does that give you false. And it's to eliminate any confusion because, yeah, English can be weird. Like if I say, am I wearing a shirt or pants? You're left going like, well, it's both. Is that, like it's a funny, it could be confusing. So we just differentiate. So if I ask you like, yeah, is the sky blue and is water wet? Well, it's true. Is the sky blue and is it over 100 degrees Celsius outside? False. Is the sky blue or is it over 100 degrees Celsius outside? Well, it's true. These are all things you're familiar with, but I was emphasizing last time, and I want to hit it again. Remember that these operators are working on the result, like the actual value that the individual statements have. What I mean is the sky blue? That's true. It's like if I said 5 plus 7 is greater than 7. I have to evaluate 5 plus 7, right? That's 12. Then I can do that operator. Same idea here. I have to evaluate what that statement is before the Boolean operator can be applied to the Booleans. So Booleans are a type in Python. You can even prove this to yourself. Print type of true. It says bool for Boolean. Mind you, it's an uppercase T. If you do a lowercase t, it'll be confused. But other programming languages will be the opposite. They'll use a lowercase t and anyways, so for Python though, uppercase T, you're fine. It says Boolean. But what's interesting about a Boolean, and I already said this before when talking about none type, what's interesting about a Boolean is it can only actually have one of two values, where an integer can have a lot of different values. It can be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, negative 45, whatever. Booleans can only be one or the other. These Boolean operators I was talking about, and, or, and not, actually, but not's not a binary operator. Not only works on one value. Is it not over 100 degrees Celsius outside? Well, who said yes? It's true. Thank you very much. Never say yes. If you say yes, just leave. It's always true or false, right? And or, those are the binary ones, meaning that they act on two values to give you back one value, where not only acts on one value, it's a unary operator. But these are just operators, like you're already used to, with like arithmetic. Plus. Plus is an operator that gives you the sum. It takes two integers, or it takes two numbers and gives you back a number. These Boolean operators, and takes two Booleans and gives you back a Boolean. It's the same idea. It's the exact same idea. It's just how they operate is a little different based on their like functionality. True and false, well, that's always false, right? True only, or and only gives you back true if they're both true. Let me ask you, I want to quiz you real quick. Am I wearing a hat and shoes? Did I even need to ask you the second half of that question for you to know the answer? No. When I said, am I wearing a hat and, it didn't even matter what I said after, right? because I'm not wearing a hat, therefore the whole thing's false, because both have to be true. Similarly with or, I could say, am I wearing shoes, or it doesn't even matter what the other one is. The or will be true because the first one was true, because all that matters is that one is true. Now, you look at a statement like this, true and false is false. It feels rather silly, right? Because why would I ever write true and false? Because true and false always gives me back false. But in the same way that 1 plus 1 always gives you back 2. So using operators like this is not that helpful a lot of the times. In reality, we're going to be using it with variables and with asking questions and whatnot. And this brings us to comparison operators. These are other operators, just like your arithmetic, just like your Boolean ones, but these ones are a little different. They're comparison operators. If I ask you the question, is it not over 100 degrees outside? True. Okay. Why is it true? Well, because not flips it, but break it down even further. So is it over 100 degrees outside? How do you know? Because it's probably less. Yeah, it's less than, right? You did a comparison. You said, okay, what temperature is it outside? Well, I don't really know exactly, but it's probably a hell of a lot less than 100. So you could make the conclusion. Yeah, these are where comparison operators come in, when you actually need to know something. If I ask you, is 5 greater than 3, what do you say? Come on, wake up. I know it's 8:30 in the morning, but what a better way to start the day than programming, right? Is 5 greater than 3? Of course, there you go, wonderful. Now, who here remembers learning about greater than and less than when you were in like grade 2? Who here remembers using it since then? Couple people, yeah, but not very often, right? It was one of those things that I remember learning, and then I was like, okay, great. Well, it's back, finally. It's useful. Great. And the good news is you should probably understand it because you've been doing it since you were pretty young. So we're in great shape. So is 5 greater than 3? True. Now let me ask you this. Is 5 greater than 5? No, it's not. It's equal to 5. It's not greater than 5. Now raise your hand if your knee-jerk reaction was true. Or is 5 greater than 5? No, no one? Okay, that's fine. But this would be an example of like an edge case. Like, well, is 5 greater than 5? Well, it's not, but it's kind of on the border, right? It's a funny one. So of course, to be more explicit, I could ask, is 5 greater than or equal to 5? True, right? And in fact, I don't even need to ask, is it greater than or is it equal to? There's a special operator to do both at once. We'll see in a moment. Is 1 greater than 7? False. So here are a quick look at some comparison operators. Equals. But mind the fact that if you want to check if things are equal, you need to use equal equal. Because a regular old equal is assignment, right? If I use the equals, it means I'm putting like some value in a variable or something. If I want to actually check if two values are equivalent, I need to use equals equals. And then that will tell me if that statement is true or false. It's a Boolean. It gives you back a Boolean. Not equal. There you go. Alternatively, you could check if it's equal and then not it. Or we just give you a quick and dirty operator for it, exclamation point equal. Often exclamation point in programming in computers means not. Greater than or equal to, less than or equal to. Of course, greater than or equal to could be done by doing these individual operators, checking if it's greater than, and then or, with the or operator, and then checking if it's equal to. But again, this just kind of skips that extra work for you. Now here's a quick activity. Open up Colab and just play with a variety of values of different types, and apply these comparison operators to them and see what you can do. See what you can actually compare, what you can't compare, and whatnot. I'll give you a minute and a half or so for this one. That's a weird one, isn't it? Is true greater than false? True. That's weird, right? Is it less than? Okay, that's neat. Is 1 less than false? What? It's really weird, right? That's weird. The Boolean one's weird, right? Does anyone know? I mean, with the values I was tinkering with, if you were watching me, you'd probably be able to figure out why. Let me put it this way. It's because false is comparable to an integer. False is 0, true is 1. I mean, traditionally, a lot of other programming languages, true is anything that's not 0, but just as an FYI, a neat little piece of trivia there. But I could say, is 7 greater than 7? Well, that's false. How about is 7 greater than or equal to 7? Yeah, so how about 7.0? It's a float. True. Is it equal to the string, or is it 7? Okay, that won't work. I can't compare an integer to a string like that, right? Okay. What about, look, this one didn't crash, though. It said false, which is kind of neat. Where if I did this, it crashes saying I can't use greater than or equal to on an integer and a string. But if I check for equality, it doesn't crash. It runs. But of course, they're not equal. Did anyone try any other combination that was peculiar to them? All right. So be mindful, like I already said, the difference between equals and equals equals. These two lines of code mean two different things. Some variable equals 5 will put the value 5 into some variable. Some variable equals 5 checks if they're equivalent. Whatever value is stored in the variable, some value, checks if it's equivalent to 5. Two very different things. If you wrote the first one and thought you were getting a Boolean like a comparison, and you were expecting some value like true or false to come back, but in the end it didn't give you back a value, it stored the value 5 in some variable, thereby obliterating whatever value was in some variable, we're going to have an issue. In fact, just as another piece of interesting trivia, some programmers do what they call Yoda notation, where if you ever want to do a comparison, never put the variable, if there's a variable and one's like a literal, never put the variable on the left-hand side. Always put it on the right-hand side. That way, if you accidentally mix them up, the program won't even run. It'll say you have like a syntax error, which is better than hitting run and then having this catastrophic potential bug of obliterating the value and replacing it with 5. If that didn't make sense, it doesn't matter. But it's Yoda, they call it Yoda notation. So instead of like some variable is equal to 5, you would say 5 is equal to some variable. I don't know. It's how Yoda would talk. I don't know. Now, all of these comparison operators, they take a value and they return something of another type. And if the types and the operators operating on those types are all correct, if they all check out, you could do whatever you want, like this right here. That statement, that first one, it's valid. Now, I don't actually even need the parentheses here because Python has an order of operations where it'll do all the arithmetic before the comparison operators. But to make it explicitly clear, I added the parentheses. But what does this evaluate to? Well, I mean, I can't just look at it and know. I have to think about it. Okay, 17 plus 2 is 19, right? So is 19 less than 18? False. Or is 17 not equal to 18? Oh, so what does that whole statement evaluate to? Come on, wake up. Who said false? Was it you? Try again. Just flip it. If it's not false, what is it? Yeah, of course. Why is it true? Well, we have a statement on the left that's false, or the statement on the right is true. So false or true, well, that gives you back a true.
So if the first statement's false, then it's true?
No, it was dependent on what the second statement was. If this was false, if I asked if 17 equals 18, and that was false, it would be false. Boolean is true if both statements aren't false. If either statement or both statement is true with or, you get back true. Just refer back to the truth table if confused. Right? The or. We had a false or true, that gives you back the true. How about this one? Is 19 less than 18? Oh, wait, no, that's me actually doing the evaluation. Look at this. I actually just did all of this. False or this, broke it down, and you get back true. So that's actually just doing each step. Here's another one. Well, is 101 equal to 100? No, well, that's false. False and, do I even care what's on the right-hand side? No. So I can just jump to false. But if we want to be nerds about it, we can evaluate it. 66 minus 17 is 49. Is 49 less than 54? Yep, so false and true, and that's still false. Is 14 greater than 0? Or is 6 not equal to 7? And is 4 plus 17 less than 20? Oof, that one's a lot, right? But all we have to do is just evaluate it. Okay, we have a true or. And then here we've got, okay, is 6 not equal to 7? Well, that's true. And then 4 plus 17, well, that's 21. Is 21 less than 20? No, that's false. And then here we have true and false. Well, that's false. Then we have true or false. Well, that's true. But again, I could have known all of this would have evaluated to true just by looking at that first true. True or anything is true. Yeah?
So this one doesn't have that issue, but like if you didn't add the parentheses around the true and the false statement at the end.
Yeah, so that one, Why don't you try it and see what it does and let me know. There another question?
Yeah, I had a similar question there.
Well, here, we can look up. I think I have a link here somewhere. Why? Yeah. I'm not sure this is the page I'm looking for here. Oh, here we go. It looks like Python will do and before or. So if I didn't have the parentheses, it would have still worked out. But if there's ever a chance of ambiguity, is adding parentheses a bad thing? No, it's a good thing, right? Make your code as clear as possible. And this right here, this is the assignment expression. Ignore the fact that it's got the colon there. This is assignment. That is the last operator that's done, which makes sense, right? If I've got some giant expression on the right-hand side, but it's like x equals some giant expression, I evaluate everything on the right-hand side. The very last thing I'm going to do is actually assign the value to the variable. Okay. And here's the thing. Now, I showed you some of these examples in practice. If your code had some crazy examples, first of all, in practice, realize that this statement is always going to evaluate to true in the same way that 1 + 1 + 1 is always going to evaluate to 3. So there's nothing wrong with these statements as is, but there's not going to be a lot of utility with the statement like that inside your code. In reality, you would have like a variable, right? Imagine you had a sensor counting the number of cars that drove by, and you would be like, well, is the number of cars greater than? That's how these are used in practice. If you ever find yourself, though, writing these long and complex expressions like this, chances are you're not doing anything wrong, but chances are you don't need to write them this complex. You can break these down into simpler, easier to follow, easier to understand expressions. So nothing wrong with that, but if the TA saw something like that in an assignment, they're going to hate you. And you don't want the person marking your assignment to hate you. So just remember that. Any questions about this Boolean stuff so far? We're going to come back to the Booleans very, very, very shortly, but the next topic is very important. Look, testing and debugging is probably like the biggest part of programming. The actual act of sitting and writing code is very small. And whenever we're writing code to solve problems, obviously the goal is to, write the code. But it's not just writing the code, it's about writing correct code. And I know it sounds like, well, yeah, no duh, but okay. So how have you been proving that your code is correct so far? No, not really, right? So if you're ever writing code, let's say you have a job in the future, you're a software engineer and you write some code for your job, right? And you're like, okay, I'm done, here you go. And whoever you give it to, your boss, is going to say, is it correct? And you're going to go, I hope so. And they're going to go, okay, go demonstrate that it's correct and come back later. You have to test your code. It is your responsibility to write the code, and it's your responsibility to demonstrate the code that you write, to demonstrate that the code that you wrote is correct. And the way we're going to do this, like so far what we've been doing is we write a function and we call it a couple of times to do like a sanity check to make sure it's correct, right? We did a couple of Celsius to Fahrenheit conversions. We printed out the result. We looked at it and we're like, yeah, it looks right. Yeah, good. But we can have a slightly more rigorous, systematic way of testing than that. There is a more systematic way to do the testing that we will be talking about later in the course, but we can't get to there right now because it's rather complex. By the end of the course, it'll be easy to learn versus now. But that doesn't mean we can't still have rigor in like a systematic strategy for testing our code. So what we want to do, I think the best way to see how we're going to do this is with some examples. But the key here is we're going to be using a keyword called assert. And assert is a keyword that will do nothing to, like, Python will evaluate the line. You know what, let me show you the example and then we'll talk about it. The absolute value function is one that you can just type in right now. Quick test. Raise your hand. Who knows what does anyone here not know what absolute value means? Okay, just in case, all it means is give me the positive value of that number. So I'm going to test you because you put your hand up real quick. -5. What's the absolute value of -5? Oh, who said 5 up there? Who said that? You're a ventriloquist. What's the absolute value of 7? 7. What's the absolute value of 13? What's the absolute value of -302? Exactly. You just drop the negative if it's there. If it's not a negative, you leave it alone. That's absolute value. Now, we're not going to see the code for absolute value because we didn't write it. But let's pretend that function was written above. And in reality, there's no need to test the functions that Python gives you. They've been tested. You can trust them. But for the point of demonstrating, I'm going to test this one here. So I'm going to copy this code. I'm going to go here, and I'm going to hit run. And we don't see anything, right? And if we see nothing with these asserts, that's a good thing. Assert will crash your program if it sees false. So when I ask, is 5 equivalent to the absolute value of 5? Is that a true or false statement? True. So we see assert true, assert's happy. How about, is 5 equivalent to the absolute value of -5? True or false? Of course. So we see assert true, it's happy. Is 0 equivalent to the absolute value of 0? True, yeah, of course. So assert true, assert's happy, it's fine. Now, with this problem here, I actually was trying to be, I didn't pick these 3 examples out of nowhere. There was a reason I picked these 3 examples for tests. Anyone want to take a wild guess? Yeah, so yeah, it's in the middle. You're exactly right. I picked a positive value as an argument, a negative value as an argument, and then 0, because 0 is kind of funny, right? 0 is in the middle. I want to make sure it does what I expect it to do. So this code is fine. Now, I'm going to show you what would happen if one of these statements was false. And the reason this statement is going to be false isn't because the absolute value function is broken. It's going to be because I wrote a bad test. Let's say I fat-fingered it and I put in a 6, right? This is an incorrect test. It's not going to fail because the absolute value function is wrong. It's going to fail because my test was wrong. And the program crashes. It says assertion error. And it even points to which one. So it told me what was wrong. And I go, no, I just wrote a bad test. I can fix that. But it crashes the program, which is a good thing. We don't want our program to be running if it's wrong. So if our program can crash, before it does some wrong calculation and carries that wrong calculation forward, and next thing you know, the Earth explodes because we made a mistake? Yeah, we don't want that to happen. We want it to break. So there, okay, we're back, we're happy. So whenever it sees something that's false, it crashes. And I could have multiple things that are false. I could type this one in wrong. I can type that one in wrong. But it'll crash at the first mistake you made. So if you go and you fix this, oh, I made a mistake. Oh, I made another mistake, right? I would have to go do it each time. Great. So here's an example of writing those tests. In reality, I should probably write a few more. I should probably do one for like 0.0. I should probably do like the exact same ones but with floats, right? We want our tests to be thorough. And they're all going to pass. Yay, good. Any questions about what you see here? I've barely scratched the surface on how we're going to use this, though, but so far, all we're seeing is the assert keyword. Okay, now, this would be how I would typically write my asserts and where I would write them. I wrote a function, okay? And then immediately below the function, I'm going to have my asserts. And then once I know it's true, I can then go like, oh, okay, now I can use it. But I go to use it and it crashes. Now this is an example of the assert test. The test was correct. If the absolute value function that I'm testing, which is called broken absolute value, which should be a hint as to where the issue might be, if that function was correct, these three tests should have passed, if the function was correct. And here's what's interesting. Imagine the absolute value function wasn't given to you for free by Python. I could write those tests before that function exists. Because if the function existed, and if it was correct, these tests would pass. So I could actually write all the tests for my functions before I even write the function. Because when I write the test, if what I'm about to write is correct, it should give me, with this input, it should give me that output, and so on and so on and so on. So why is this broken? Well, I wrote an absolute value function that is broken. Because all it does is it just returns x. So if I give it a positive number, it gives me a positive number. If I give it a negative number, it's going to give me a negative number. But if this was correct, the three tests below should pass. There's nothing wrong with these tests. The issue is with the function. And it tells me, look, it crashes. And it crashes on the negative case. These tests, if they fail, they actually help you know what's wrong. Because I look at this and go, okay, it was fine in the first case. So clearly it seems to be fine with a positive value. It's with the negative value there's the issue. Okay, all right. So the tests not only tell you if you're right or wrong, it actually points you in the right direction. If everything's going well, it points you in the right direction of where the issue is. Because whenever you're writing code, you're writing general code. And you're going to test it with specific cases. But maybe some of those specific cases will be correct, and some of them won't be. And here's an awesome thing too. Let's say I wrote these tests, and then sometime in the future, you know what, I'll give this example once we go a little further with more concrete examples. Yeah. Yeah, so this is telling you that the test failed. More precisely, it failed on the -5 case. This informs us the function is correct and under which condition it's not correct. So here's an example of square of sums. This was a function we wrote in the functions topic. And notice I wrote that docstring, right? Remember I talked about docstrings at the end of the function topic? You always describe what's going on inside your function. It's right below the def line, but before all the relevant code. I describe what's going on in that function. I describe the parameters, and then I describe what it's going to return. All right? Now, if I go down here, I see several tests. Without even looking at the code, and I say to you, imagine you have a function that takes two values, sums them together, and squares it and gives you back the result. Knowing what the function is supposed to do, you can write all these tests. You don't need the function. If I called it with 0, 0, I should get 0. If I get 1, -1, I should get 0. If I get 5 and 5, I should get 100. If I get -5, -5, I should get 100. And then this bottom one here is a funny thing, because assert is a keyword that's looking for a Boolean value. And then you're going to say, well, no, you don't have a Boolean value there. You have like a comparison expression. Yeah, but that comparison expression evaluates to a Boolean. Right? Remember, it's always about what it evaluates to. So because computers are really bad with floating point numbers, with decimals, and comparing them, a lot of issues can come up. This is what I mentioned a couple weeks ago. And I said we'll come back to it. If we're ever comparing floating point numbers, don't. What you do is you take the absolute value of the difference between the values I'm trying to compare, and I check if the difference is small enough. And small enough is the threshold I make up. So if you look here, I'm checking, okay, square of sum of 2.2, 2.2, should be 19.36, right? It should be. But the problem is there's a floating point number there, and that could cause issues for the computer. So what I do is I take the difference between the two. I take the absolute difference between the two, meaning I don't care if it's positive or negative. I just want to know how different they are. And then I check if that difference is less than some threshold. And in this particular example, my threshold was 0.001. I came up with that threshold. I picked it out of wherever, but really you would pick the threshold based on what you're currently doing and what's fine. If you're working with high precision instruments where you have a lot of accuracy, oh yeah, okay, maybe 0.001 isn't very good. If you're dealing with like distances in kilometers, and you don't have any higher precision than kilometers, right? Like if I'm like, oh, you know, it's like 3 kilometers for me to get to work, right? Well, it's not really 3 kilometers. It's probably 3.2 kilometers or something, but I only said 3. So there's no need for me getting any more precise than that, right? That'll be good enough. If I'm working on the space station, that's probably not good enough. But cool? Yeah? That's how we do the asserts. That's really how we do comparisons for floating point numbers. Check if the absolute difference between the things you want to compare is small enough. Any questions about that? So there we go. I hit run, and everything passes. This is great. If you gave me this code, and I look at it, and all I really do is I look at the test and be like, look, if I hit run and they all pass, you're almost certainly correct. You're not guaranteed to be correct. Maybe you didn't write thorough enough tests. Maybe in some peculiar case you could be wrong. I don't know. But you're almost guaranteed to be correct. And this is what's awesome about programming. And I said it at the beginning of the semester, but now it's probably even more explicitly clear, because when we write tests, before you submit your assignment, you could know if you're right or wrong. There's no mystery. There's no, I think I'm right here, I'm submitting it, I hope I get a good mark. It's, if you hit run and all your tests pass, chances are you're near perfect, if not perfect. That's great. Not very many disciplines have that luxury, right? This is fantastic. You can know you're correct even before you're done. I love it. Another thing that's cool about these tests, this is what I was going to say earlier, but now that we have an example. Let's say, for whatever reason, this code you wrote is super important. It's on the space station. And someone needs to update this code. And maybe they update it. For whatever reason, they did this. Maybe they had a typo. Who knows? But somehow that function changed. It shouldn't have been changed, but it got changed. And it's got changed so that it's going to be incorrect, right? Clearly that's not going to be right. Well, if I always allow the tests to run, it's going to tell me, like, oh, wait, why did that break? It was fine before. What the heck's going on? And you go, oh, that's weird. So by having the tests there and always running, you are always ensuring that those functions are always working. You might say, well, I tested it last week. Great. But is it correct today? Well, I don't think I changed it since then. Great. But is it correct today? Always just have the tests there. There's no mystery on if you're right or wrong. This is great. Any questions so far about these tests? I think they're great. From now on, now in the assignment, I give you the tests at the end of each function, right? So if you load up your assignment and you hit run, all the tests are going to fail because you haven't written the functions yet. But I give you tests. So if you write your code and you hit run and all the tests pass, chances are you nailed it. That's great. But whenever you write a function, if it's lab, if it's wherever, write your cert tests. You don't have to do it on your tests, like your written tests, right? Don't worry about that there. But whenever you're writing your code, always write your tests. If you're like, I'm having a hard time, if you're in lab or you come to student hours and you say, I'm having a hard time, there's something wrong with my code, I can't find it, and you show it to me and I don't see tests, I'm going to say, okay, go write your tests and then come back once you did. Because you're trying to skip a step. Writing tests, very important. You haven't finished writing a function if you haven't written your tests. Cool? I think it's cool. Now, writing tests, you try to make sure your tests are accounting for all possible cases. I probably didn't here, right? Maybe I should have checked two negative floating point numbers, a negative and a positive, floating point numbers with different value, whatever. There could have been a lot more tests here. But of course, you don't need to get crazy with the number of tests you write. There's no sense in writing 100 tests for sum of squares. But you want to make sure your tests are as thorough as possible. Writing tests, though, and being able to think about all possible cases for that function is a bit of an art. This is a skill, an intuition you develop as you go. You're not going to be pros at the beginning, but the more you do it, the easier it gets for you. So don't worry. When you come to student hours or you're in lab and you're like, oh, blah, 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 and I see your tests, and maybe you're missing a case and that's the issue. I'm not going to chastise you for that, of course. You tried, you're learning. But if I don't see any tests, I'm unhappy. And then you might say, well, I didn't finish writing the function, so how could I write the tests? But didn't I just finish showing you that you don't even need to have a working function in order to write the test for that function if you know what that function is supposed to do? And if you don't know what that function is supposed to do, why are you writing it? No, if you're writing a function, you better know what that function is supposed to do before you write it. No sense in sitting down and being like, I need a function. What is it going to do? I don't know. That's silly. So you can always have your tests. There's no reason not to have your tests. There's no reason to not, the reason to not have a test is if, like, we didn't have to test the print function, right? Python gave it to you. We should be confident in that it works. And if it doesn't work, is it your fault? No, it's Python's fault. Yeah. And this is just me talking about try to get as many cases as you can. And the reason we want to have as many cases as you can is because, well, then you're testing it thoroughly. But if it fails on a specific case, then it tells you, oh, it doesn't work when only one number is negative. That's weird. And then you can go, it gives you a hint as to where the issue is. And this goes to the floating point number thing, right? If I run square of sum 2.2, 2.2, the answer is 19.36, but Python's going to say, no, it's 19.360000000003. And you remember I explained, raise your hand if you remember me explaining why. Okay, I'll just say it again, just so everyone at least remembers. This isn't on the test, but I'll explain it. And maybe as I start explaining, it'll come back to you. I need everyone to work with me here. So shout out the answer when I ask the question. What comes after 1? What comes after 2? What comes after a million? What comes after a bajillion? Exactly, right? There's no mystery. But now if I ask you the same question with real numbers, meaning there's decimals, what comes after 1? Yeah. Is it 2? No, we missed 1.1. Not to mention 1.2. Okay, so is it 1.1? No, you missed 1.01. So we've got an issue here. And these computers can only store a finite number of values because of the limitation of how they're built. There's nothing in the realm of computing, never mind, but really, the fact that I can't store a number like 5 trillion in your standard computer very easily is not because the computer is bad at math. It's because, well, there's so many transistors and so many bits that it's working with. And there's a finite number of integers that your computer's happy with. I'm speaking traditionally, by the way, because programming languages have hacks for this. But if I have a finite number of integers, I also am going to have a finite number of floating point numbers I can represent. And there's also, we kind of established, there seems to be a hell of a lot more floating point numbers than there are integers. We're going to have issues. So the way the computer deals with it is it goes, close enough. Long story short. But of course, that can create issues when you're like, well, if I want to check if square of sum 2, 2 equals 19.36, it's going to say it's wrong, even though it's right. Well, that's why we do that trick of calculate the absolute difference between the things we actually want to compare and check if it's smaller than a threshold. If the difference is small enough, we'll call it even. It's the same issue, and I asked it before. It's the same issue of what's the probability of it raining exactly 1 millimeter today? Who can answer that? There's a very specific answer. No one knows? What? 50%? No. There is an answer. You don't need to know what the chance of rain is today to know what the probability of it raining exactly 1 millimeter is. What? I like what you're thinking. The answer is 0. It's a hard 0. Because did it rain 1 or 1.1 or 0.99999 or 1.0001? That's why in like probability, remember when you're comparing like discrete distributions, you can just count. But whenever you have a continuous thing, you got to integrate. Ugh. It's the same idea. That's why when you want to know whenever you want to know the probability of a continuous value, you always have to give a range. So like, what's the probability of it raining 0.99 to 1.01? And then what's the probability of that? Well, then you'll get an actual number. But because of real numbers, there's just too many of them. We can't deal with it. So it's a related problem, which I find fascinating. There we go. Cool. All right, we'll stop there.